Gravity is the silent architect of our universe, an invisible force that quietly sculpts the cosmos from the grandest galaxies to the tiniest particles. Imagine for a moment, you are standing on the surface of our planet, feeling the reassuring pull of Earth beneath your feet. That gentle tug, so familiar you barely notice it, is the same force that binds distant stars together, holds planets in their orbits, and shapes the fate of everything that exists. But gravity is much more than just a simple pull. It is the very language the universe uses to communicate, a conversation woven into the fabric of space and time itself. To understand gravity, we have to let go of our everyday ideas. For centuries, scientists pictured gravity as an invisible force acting between masses, like a string pulling two objects together. But in the early 20th century, Albert Einstein shattered this view with a revolutionary insight. Gravity is not just a force, it's a curvature of space-time. Picture space and time as a vast, stretchy fabric. When a massive object like a star or planet sits on this fabric, it creates a dimple, a curve. Smaller objects roll toward these curves, not because they are being pulled by some invisible hand, but because the very shape of space guides their paths. This is the heart of Einstein's general relativity, a theory that rewrote our understanding of the universe. General relativity posits that gravity is an intrinsic geometric property of a four-dimensional continuum known as space-time. Unlike Newton's view, which described gravity as an attractive force acting between masses, Einstein's theory illustrates that massive objects and concentrations of energy cause a distortion or curvature in the fabric of space-time. This curvature, rather than a mysterious force, is what directs the motion of everything within its influence, including light. In this geometric interpretation, phenomena traditionally ascribed to the force of gravity, such as the free fall of an apple or the orbital motion of planets, are understood as objects following the straightest possible paths, known as geodesics, within this curved space-time geometry. There is no external gravitational force deflecting objects. Instead, their paths are a natural consequence of the altered geometry of the space and time they traverse. This concept is eloquently summarized by the aphorism, "Space-time tells matter how to move, matter tells space-time how to curve." This shift from gravity as an external pull to an intrinsic property of the medium itself marks a fundamental change in how physical interactions are modeled. It implies that the universe is not merely a passive stage for events, but an active, deformable entity, which profoundly alters our understanding of all physical interactions and is crucial for comprehending extreme phenomena like black holes and the very beginning of the universe. For weak gravitational fields and objects moving at speeds significantly less than the speed of light, general relativity's predictions converge with those of Newton's law, effectively encompassing classical gravity as a limiting case. Now let's travel to the edge of a black hole, one of the universe's most extreme laboratories. Imagine a place where gravity is so intense that it warps space and time to their breaking points. Here, light itself cannot escape. If you watched a clock at the edge of a black hole, you'd see something strange. Time slows down. Minutes stretch into hours. This phenomenon is called time dilation. The stronger the gravity, the slower time passes. In our everyday lives, this effect is tiny, almost unnoticeable. But near a black hole, it becomes dramatic. A reminder that time is not a universal constant, but a malleable dimension shaped by gravity. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape their grasp. They typically form when an object's mass is compressed into a sufficiently small volume, leading to a critical mass-to-radius ratio. The most common type, stellar mass black holes, are the collapsed remnants of massive stars that have undergone a catastrophic supernova explosion. On a far grander scale, supermassive black holes, with masses ranging from millions to billions of solar masses, are believed to reside at the center of nearly all galaxies, including our own Milky Way. The defining characteristic of a black hole is its event horizon, a boundary often conceptualized as its surface. This is the point of no return. Once anything, including light, crosses this boundary, the escape velocity required to leave the black hole's gravitational pull exceeds the speed of light, effectively trapping it forever. While black holes themselves do not emit or reflect light, astronomers can infer their presence by observing the light emitted by surrounding matter that has not yet succumbed to the event horizon. At the very heart of a black hole, general relativity predicts the existence of a singularity, a point where matter is crushed to infinite density and the gravitational field becomes infinitely strong. At this theoretical point, space-time itself is predicted to break down or be ripped apart, and the conventional laws of physics cease to apply. This pathological nature of the singularity, where space and time effectively cease to exist, represents a major conceptual challenge and suggests the limitations of general relativity itself. Black holes thus represent a duality. They are triumphs of GR's predictive power, yet their very core highlights the theory's incompleteness, necessitating a more complete theory, such as quantum gravity, to fully describe these extreme cosmic objects. This directly addresses how our understanding of gravity and quantum mechanics strains at black holes. The extreme gravitational field of a black hole profoundly warps the surrounding space-time, leading to visually striking phenomena. This warping causes light to follow distorted paths, a process known as gravitational lensing. This effect can create multiple, highly distorted images of background objects, or even the black hole's own accretion disk. The accretion disk itself, formed by gas and dust spiraling inward, is the primary source of light observed from black holes. When viewed from various angles, the accretion disk can appear to have a funny shape due to this lensing, with light from behind the black hole appearing as humps above and below it. The combination of the event horizon's ability to capture light and the extreme space-time distortion around it results in a dark region known as the event horizon shadow. This shadow, roughly twice the size of the black hole's actual surface, is a direct visual manifestation of the space-time curvature and the boundary beyond which light cannot escape. Black holes grow by consuming matter through accretion or by merging with other black holes, processes that can also lead to the emission of highly energetic particle jets that blast away from the black hole at near-light speeds. These phenomena provide tangible, observable evidence of space-time curvature in action, making the abstract concept of warped space-time concrete and allowing astronomers to see the effects of black holes, even though the black holes themselves are invisible. Black holes are not merely cosmic curiosities. They play a crucial role in the evolution and dynamics of the universe. They exist in various mass ranges. Primordial black holes. Hypothetical, formed in the very early universe, potentially ranging from tiny to large masses, though none have been conclusively detected. Stellar mass black holes. Typically 5 to 100 times the mass of our Sun, these are the most common type, forming from the gravitational collapse of massive stars. Intermediate mass black holes. Ranging from hundreds to hundreds of thousands of solar masses, these are thought to bridge the gap between stellar and supermassive black holes, with evidence for a few candidates. Supermassive black holes. Millions to billions of solar masses found at the centers of almost all galaxies, including the Milky Way. They are believed to be crucial in galaxy formation and the development of larger cosmic structures. This idea that time can bend and stretch is not just science fiction. It is a real, measurable effect. Even here on Earth, time ticks a little faster on a mountaintop than at sea level because gravity is weaker higher up. Our GPS satellites, orbiting high above the planet, have to account for this time difference to keep our navigation systems accurate. Without Einstein's insights, your phone's map app would quickly lose its way. Time dilation, in its most general sense, refers to the difference in elapsed time measured by two clocks. When the term is used without further qualification, it typically refers to the effect caused by relative velocity, as described by special relativity. According to special relativity, a clock that is moving relative to an observer will be measured by that observer to tick more slowly than an identical clock at rest in the observer's own frame of reference. The greater the relative velocity between the clocks, the more pronounced this time dilation effect becomes, theoretically reaching a point where time would appear to stop if a clock were to approach the speed of light. A fascinating aspect of velocity time dilation is its reciprocity. If two observers are in relative motion, each will perceive the other's clock as ticking slower than their own local clock. This might seem paradoxical, but it is analogous to the effect of perspective, where two people observing each other from a distance will each appear small to the other. There is no contradiction because each observer is in their own inertial frame of reference. This reciprocity is central to understanding the famous twin paradox, where one twin embarks on a high-speed space journey while the other remains on Earth. Upon reunion, the traveling twin will have aged less. The resolution lies in the asymmetry of their experiences. The Earthbound twin remains in a single inertial frame, while the traveling twin undergoes acceleration, thus moving between different inertial frames. This demonstrates that time is not a universal constant, but an observer-dependent dimension, challenging our everyday intuition about the absolute nature of time. But gravity's story stretches far beyond black holes and satellites. It reaches back to the ultimate beginning, the Big Bang. 13.8 billion years ago, the universe exploded into existence from an unimaginably tiny, hot, and dense point. In that first moment, space and time themselves were born, along with all the energy and matter that would eventually become galaxies, stars, planets, and life. Gravity was there from the very start, orchestrating the expansion and shaping the cosmos as it cooled and spread out. The cosmic web we see today, the vast tapestry of galaxies connected across billions of light years, is gravity's handiwork. According to the Big Bang Theory, the universe originated approximately 13.7 billion years ago from an extremely small, hot, and dense state. Since this initial moment, the universe has been in a state of continuous expansion, leading to its decreasing density and cooling over time. A cornerstone of this theory is Edwin Hubble's discovery in the 1920s, which established a direct relationship between a galaxy's distance from Earth and its speed of recession, a principle now known as Hubble's law. This was observed by analyzing the spectroscopic redshift of light from distant galaxies, indicating they are moving away from us, with more distant galaxies receding at faster speeds. It is important to clarify that this expansion does not mean galaxies themselves are growing larger. Rather, it is the space between galaxies that is increasing, causing them to move further apart. This phenomenon is often likened to dots on the surface of an expanding balloon, where every dot moves away from every other dot and those farthest apart move the fastest. This dynamic nature of space-time on cosmic scales, where the very fabric of the universe is evolving, is a direct consequence of the interplay between matter, energy, and space-time geometry, demonstrating general relativity's applicability to the entire cosmos. Yet, as we peer deeper into the universe, we encounter a strange paradox. The laws that govern the very large, planets, stars, galaxies, are ruled by gravity and described beautifully by general relativity. But when we zoom into the smallest scales, the world behaves according to a very different set of rules. Quantum mechanics. Here, reality is jittery and unpredictable. Particles pop in and out of existence. Space itself is not smooth, but foamy and chaotic, like the surface of a boiling pot. This is quantum space, a realm where our classical intuitions break down. General relativity and quantum mechanics stand as the two foundational pillars of modern physics, each having achieved unparalleled success within their respective domains. General relativity provides a comprehensive framework for understanding gravity and the universe at large scales and high masses, encompassing phenomena from the orbits of planets to the dynamics of galaxies and the cosmos as a whole. In contrast, quantum mechanics successfully describes the universe at very small scales and low masses, governing the behavior of subatomic particles, atoms, and molecules, and accounts for the strong, weak, and electromagnetic forces. The core incompatibility between these two theories stems from their radically different underlying principles. General relativity operates within a framework of smooth, continuous space-time, treating gravity as a geometric manifestation of this continuum, and is largely deterministic in its predictions. Quantum mechanics, conversely, is inherently probabilistic, describing reality in terms of discrete particles and quantized energy levels. Attempts to describe gravity within the quantum mechanical paradigm often lead to mathematical inconsistencies, such as the appearance of infinite values for certain physical quantities, indicating a breakdown of the equations. These breakdowns become particularly acute under extreme conditions. such as the interior of black hole singularities or the very early moments of the Big Bang. This profound conceptual chasm between the macroscopic and microscopic descriptions of reality means that our current understanding of the universe is fragmented. Neither theory alone can fully describe phenomena where both extreme gravity and quantum effects are significant. The ultimate goal is the development of a unified theory, often referred to as a theory of everything, that seamlessly integrates all fundamental forces and forms of matter into a single, coherent framework. Black holes sit at the crossroads of these two worlds. They are massive enough to warp space and time, yet small enough that quantum effects can't be ignored. Inside a black hole, our theories collide, and so far, they refuse to fit together. This is the frontier of modern physics, the quest to unify gravity with quantum mechanics, to find a theory that describes the universe from the largest scales down to the tiniest. Scientists are hunting for clues in the behavior of black holes, the echoes of the Big Bang, and the subtle ripples of gravitational waves. Faint tremors in space-time, first detected in 2015, which confirm yet another of Einstein's stunning predictions. When you learn about gravity, time, black holes, the Big Bang, and the quantum world, you are tracing the deepest threads of reality. Each concept is a window into how the universe truly works, how galaxies spin, why time flows differently in different places, what happens at the edge of existence. You realize that the universe is not a static backdrop, but a dynamic interplay between the large and the tiny, the smooth and the jittery, the known and the mysterious. Think about this the next time you look up at the night sky. Every star you see is locked in a cosmic dance, its path shaped by gravity. The light from those stars crosses billions of years, bending around galaxies, slowed and stretched by the curvature of space. Somewhere, perhaps, a black hole lurks, its presence revealed only by the way it warps the world around it. And beneath it all, at the smallest scales, quantum fluctuations are constantly bubbling, reminding us that even empty space is never truly empty. These ideas are not just abstract theories. They touch our daily lives in subtle ways. The same principles that govern the fall of an apple also guide the GPS signals in your phone and the life cycles of stars in distant galaxies. Understanding gravity and its companions, space, time, black holes, and quantum mechanics, gives you a new lens through which to see the world. You begin to sense the hidden connections, the invisible glue that holds everything together. Embracing these cosmic concepts is an invitation to curiosity. It's a way to feel more connected to the universe, to appreciate the elegance and mystery that surrounds us. Whether you're marveling at a sunrise, pondering the age of the stars, or simply wondering why time seems to flow the way it does, you're engaging in an ancient quest, a desire to understand our place in the grand tapestry of existence. So the next time you feel the pull of gravity, remember, you're not just feeling a force. You're touching the very fabric of reality, shaped by billions of years of cosmic evolution. You are part of a universe where space and time bend, where black holes hide secrets, where the smallest particles dance to quantum rhythms, and where every moment is linked to the grand origins of all things. To explore gravity and its mysteries is, in the end, to explore yourself and your connection to everything that is.